What it do, everybody? Welcome to the third part of this video. Up until now we found out many of the stuff, but we have not yet stumbled upon the solution to this kata. So let us read this clue right over here about why does this FSM work to accept only numbers that are divisible by 3. So it says states A, B and C correspond to inputs congruent to 0, 1 and 2 modulation 3 respectively. Modulo. Suppose that the input so far represents a multiple of 3 so that you're in a state A. A 0 multiplies the current number by 2. Chunk. So it's still a multiple of 3. And you're still in state A. A1 multiplies it by 2 and adds 1, making it congruent to 1 modulo 3 and putting you in state B. Yo, what the hell, man? I don't understand that. I do not understand that. If the current number is congruent to 1 modulo 3, so that is for example 4, you're in a state B. An input of 0 doubles the number, making it congruent to 2 modulo 3, and you're taken in state C. And input of 1 on the other hand doubles the number, making it congruent to, again, to 2 modulo 3 and then adds 1, making it to a multiple of 3 and sending it to a state A. I do not see where. Oh, 0 and then 1, I guess, I don't know. In the same way, you can analyze what happens when the current number is congruent to modulo 3 and you're in state C. Doubling the number makes it congruent to 4 and hence 1 modulo 3 and moves it to a state B. Alright, so we established that state like 1 modulo 3 is for example 4 and that is state B. So I guess then C is 2 modulo 3. Thus, the 3 states really are connected properly. All of this boils down to what I see. Ted. Where's Ted? Oh, right over here, I'm giving his answer. When you read a bit B, you're shifting. When you read a bit B, you're shifting the current number one place to the left, which multiplies it by 2, and then you're adding B. The FSM mimics the effects of that operation on the residue of the number modulo 3. So that's by 2 and then adds B. The above diagram performs that operation modulo 3. Well, Ted made a really short answer. Maybe it's just Ted Kaczynski, the genius, you know. That's a joke. Take it as a joke, because it's a joke. Alright, so we see I kinda get a tiny teeny little weeny bit, and it's starting to dawn on me that this is only for binary numbers, because I thought that this maybe is for ordinary numbers. So this finite state machine accepts binary numbers that are divisible by 3. Now, it would be very good if I had this over here, because it would be relatively easy to make. I mean, alright, even this is hard to make as a regular expression, but that's just another step, and if we don't have this image, then that step is missing. So let's go to the Wayback Machine. to see if we can find this URL in the Wayback Machine. And if we enter a URL, find that, failed to fetch, failed to fetch, failed to fetch, failed to fetch. Yo, this is just dot Switalski, Switalski, what Switalski. Nah, I don't want .github.io. Oh my god. Oh my god, man, how these URL search bars frustrate me. Alright, Switalski is this guy again. Sorry, I don't wanna like display the image of his kid, man. I don't know why he does that. Image, yeah, image. Yeah. Empty image. Oh my god, it's an empty image. History. History. Edit. You just added it and then it's invisible, man. Was it like copyrighted or what? It's like 32 kilobytes big file that apparently cannot be seen. Ah. Oh no. Maybe that's just me. Ah, look, oh my god, I see it. Oh, I found it. And it's the same one. Oh my god. It was just transparent. Oh lord. Oh lord. Look, actually we can't see it. My screen is just too dirty. Oh my god. Oh my god. Look, we just take background color and we turn it to, what should we turn it to? Like FFFFF, right? So it's white. Here it is. Oh my god. Oh my god. Oh lord. Oh my god. Okay. I need a moment to collect myself from this surprise. Oh lord. Like, did he do that on purpose? Why did he do that? Like,
Hey, you also need to know some HTML and CSS to finish this kata.
oh my god. Alright. But this is the same as we found ourselves on Google, you know. So it's the same. But I realized, like, before I said, oh, I do not understand it because it does not have a starting point. Like, for example, this one has this start, and this is, what did we call it? Accepting state. Like, this thing does have an accepting state but not starting state. And I think that is because there are all of this stuff can be a starting state. Because it can be, and this should be also the starting state, you know. So let's start at 0, and if we go 0 multiple times, it's still divisible by, it's still like 5, you know. But we can go, if it like starts with 1 and then 0 and then 1 and multiple times, that is written like so. Damn, alright. Fine. Fine. So this, but this test is making me confused. This should be a false positive, or I don't know, something false. I don't know. Let's see it. Let's see this. It's decimal to binary. Oh no, binary to decimal. Never mind. We can switch it up. Boom, 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 boom. Convert. Yeah, that is false. Okay. Okay. So this stuff here is expressed, and we need to also express all of these things. And that's why I'm gonna read this later. That's an interesting essay right over here, and an interesting website overall. Yeah. So what do we need to do is to just like translate this finite state machine to regular expressions, or just express this finite state machine in terms of regular expressions. So this is partial solution, but the whole concept is still eluding me, kind of, because okay, we must express. We're at 0. And I guess we're looking at from this way up back there, or like we've watched Barry's videos, and what Barry did is he started at the regular expression and then wrote a finite state machine from that. Now we must do the opposite. Now we must do the opposite of that. And a starting state is elusive. Let's make a Google search. Yeah, what's with these two guys, man? Why are you promoting me, American Eagle? Why, man? Why? Come on, customize background image. I do not want to see sponsored images. Alright, fixed it. That was easy. Like, so create regex from FSM, finite state machine. It's and Ivan Zuzak, FSM2 regex, yo. Alright, let's rest our eyes. Let's RESAT. Nice. Our eyes are refreshed. So this one says, convert your FSMs to regexes and your regexes to FSM. Create automation. Enter a FSM below and the application will convert and show the equivalent regular expression. Alternatively, enter a regular expression and equivalent FSM. Okay. Enter an FSM into the okay, and it shows you. Oh my god, it's so interesting. Enter FSM into the input below or click generate random DFA NFAE NFA to have the app generate a simple FSM randomly for you. Next, click automation. A valid FSM definition contains a list of states, symbols and transitions. the initial state and the accepting state. Yeah, we do not have the initial state at this one. Where is the initial state? Like, how to, like, FSM does not have an initial state. Like, just like this one. Short answer. Oh. Huh. That's some MIT stuff. Uh-huh. What's a Moore machine? Moore machine. I guess this is a Moore machine. Like what we have been dealing with right now. Maybe it's a type of a diagram. Let's see the definition. It's a finite state machine whose output values are determined only by its current state. Whose output values are determined only by its current state. Only by its current state. That could mean that current state. Yeah, but more. Yeah, look. Moore machine still has a starting point. You know, starting point. I guess no starting point. So. Starting point could be anywhere, you know. Alright. Is there a tool or algorithm? There are several algorithms. Like, yeah, I mean, alright, we can generate random one if and states. Alright. Let's try to make that like DFA. Now I don't know what's the difference between NFA, DFA and stuff like that. Let's see. Difference between DFA, NFA and ENFA. Yeah, geeks for geeks again, yeah. Deterministic finite automation, non-deterministic. Let's see. ENFA has a starting state and an accepting state. This one has accepting state and starting state. Every one. Oh, all right. Gramophone. Ivan Zuzak. Noam. What's Noam? Noam is a JavaScript library for working with automata and formal grammars for regular and context-free languages. Noam's name comes from Norman Chomsky and his hierarchy of formal languages and grammars. Yo, this is interesting. Yo, I find so many interesting things on the internet. Who's this guy? Where's he from? He's from Zagreb, Croatia. Well, what's up? Big up yourself, Ivan. Yeah. So, all right. Let us try. I mean, can use empty string. Can be understood as one machine, multiple little machines. Next possible state is distinctively set. I mean, oh. Yo. All right. We could say there are, I don't know, there are like 5 states, S3, S4, there's 5 of them, you know. Initial is S0, accepting there's, oh no, there's no initial ones. And it's missing section, you know. There's no initial, you know. Is not a state of the SFM. Just delete that. What you gonna do now? Accepting is 1. Like, I think this one is like lacking. But if you think logically, you know, you should work the end is also the beginning, you know. So this is as starting as, because you want to make a regular expression that starts here and also returns here. So let us make a expression that starts here and also finishes here, you know. So that would be like either is 0, either is 1, 0, 1, and then again 0 multiple times. And I guess 0 here is also 0 all or multiple times. Okay, and we got a bunch of errors because of our little involvement. Alright, so after the first one we can have, like, we're at this state right over here, and there can be 0, which can follow, or we can add 1. Alright, I mean, I'm gonna make another break over here because I realized how I'm gonna do it, and I need to refresh myself a little bit because it's I need a clear head because I see it, it's right in front of me. So see you in a bit, bye!